underlying any phylogenetic tree has to be an evolutionary model. So what we can look at is methods used to model sequence evolution. So distance methods try to find the mean number of changes per site since the most recent common ancestor between any pair of sequences. Now the problem is that each sequence is changing and they might not be changing at the same rate. For example, if I'm looking at two mammalian species, so I'm looking at mice and elephants, elephants have a much longer time living compared to mice, so mice are going through more generations for the same time that elephants are. So if you imagine that mutation occurs for a certain length of your genome for a certain number of generations, so you'd expect there to be more mutations in mice than there are along the chains going towards elephants. So simply counting the number of differences, which is the p distance, may underestimate the amount of change, especially if there's either a lot of dissimilarity. You can end up with hidden changes. So things have changed and then changed again and then to maybe change back, which means you're missing things which are actually there. They're hidden from view because of the evolutionary distances. This is when it can be a good idea to use protein rather than looking at nucleic acids. You need to have models which reflect the parameters of how we think evolution might have occurred. We have different levels of models and scoring matrices dependent on how complex we wish to get. They can be used for distance models. They can also are applied in maximum likelihood models, which are parsimony based models. The most basic of all is called the Jukes-Cantor model. The most complicated of all is the general time reversible model, which gives different probabilities for each one of the particular changes. There's also a model which is rather obscure called the log-DT paralinear distance model, which was intended to deal with some very specific cases within specific programs. Generally, what we're going to consider is the Jukes-Cantor, then going through ones which have transitions and transversions with different probabilities, which is HKY, and some other steps that lead between Jukes-Cantor and the ultimate, which is GTR. Now, depending on the size of your data set and how many sequences you have, depending on how likely it is you can calibrate each of the models effectively. Another thing that you need to deal with is site rate heterogeneity, so dealing with the gamma correction. What we use is called a gamma correction. So you know the codons, the first two codons do not change as often as the third. So what we can do is fit a probability distribution to the three different positions. So 0, 1 and 2, which is the same as 1, 2 and 3 in the codon positions. So what you want is a low probability of a change at 0, low probability at change of 1 and a high probability at 2. So what you can do is tweak what's called the gamma distribution to fit something which will give you the probabilities across these ranges. Now, I talked about the Jukes-Cantor model, the simplest one, actually not as old as you imagine, first proposed in 1969. It assigned an equal substitution rate of alpha to all the bases in 1 unit of time. So below is a Markov chain diagram showing the transition. So A goes to A 1 minus 3 alpha time. For A to go to G, the probability is alpha. For A to T is alpha. A to C is alpha. From T to A is alpha. All of those connections have a probability alpha, and of it remaining the same is 1 minus 3 alpha. So what you can do is figure out the distances xy between a sequence X and a sequence Y by the number of changes per site. Remember that sequences are of different lengths, so you have to calculate the number of replacements divided by the number of sites. So if I have a sequence which is 100 long, it's going to have it's going to have more changes than one that's 1,000 long. because evolution happens 1 in 10,000 bases. If I got close to 10,000, then I'm getting close to having 1 guaranteed each time. In fact, I think it's less often than 10,000. I think it's 10 to the a lot more than that. So P is the observed proportion of nucleotides that differ between the two sequences. It's also known as the fractional dissimilarity. Ln is the log natural function to correct for superimposed substitutions. There is a complete derivation of this if you want to go through it, and I can provide you with it, but the thing that matters at the end is the distance between the two sequences equals minus 3/4 log natural of 1 minus 4/3 p, where p is this ratio of differences. Now, what Jukes-Cantor doesn't deal with is over very long distances. Here we've got two sequences, and we're just going to look at the position A in the two sequences. That's the same in both of them. So imagine that A arose by, in sequence 1, it goes C, goes to G, goes to T, and then comes to A. Nice. And in sequence 2, it arose from an ancestral sequence which was C and just went directly to A. When you have sequences that have a very long distance between them, you miss a lot of the changes that happen. It gets very hard to infer what the intermediates are over millions of years and millions of generations. Jukes-Cantor is very basic. It's better to do a more realistic model, and you can do more realistic models when you have more data. The more data you have, the more variables you can calculate and fit to your model, because you've got more data to support the creation of that model. So we can go from Jukes-Cantor to more complicated things, and eventually when you've got hundreds or thousands of sequences, then it makes sense to use the general time reversible model. If you want to look into this in more depth, there's a couple of very good YouTube videos going through evolutionary models.